we finished at this point last time.
Yeah.
Okay. Now let's move to the physical properties of the ionic compounds. Ionic compounds. What are the physical properties of the ionic compounds in general? These are the high melting temperatures, brittleness, poor electrical conductivity when solid but good when molten, and often soluble in water. So what is brittleness here?
And snap easily.
Sorry?
And can break or snap easily.
We can break or snap easily. Okay, break, or in other words, to fracture any substance. That is brittleness. So the ionic compounds can be easily broken into two parts or multiple parts by applying some force. So we'll study this in the form of the diagram. So considering the first point, melting temperatures, the ionic compounds have very high melting temperature, and it is because there are very strong electrostatic forces of attraction between the oppositely charged ions. The positive ions and negative ions are attracting each other with very strong forces. So that's why they show very strong ionic bonds, and those ionic bonds cannot be broken easily by less temperature or energy. So that's why very high energy is required to break those electrostatic forces of attraction. Clear?
So,
All right, and then about the brittleness. This is the brittleness here. Brittleness means what? That whenever a force is applied on a part of the ionic structure, then what happens? That one layer of the cations and anions, they slide past from one another, and as a result, the similar ions come in front of each other. So positive ions come in front of the other positive ion, and negative ion come in front of the other negative ion or the other layer. And what happens when the ions of the same type come in front of each other? This is happening in the brittleness, that the layers are splitting apart from each other. Is it clear?
yeah.
Okay, then the other part is about electrical conductivity. The electrical conductivity means, as we know, that the ionic compounds contains the positive ions and the negative ions. So will the ionic compound conduct electricity when they are in this structural form, or we can say in their solid form? Will they conduct electricity?
No.
Why?
Because there's no movement of electrons, charges not flow.
There is no movement of electrons. Electrons
Yeah.
of the electric current or the electrons of the ions?
Electrons of the ions, so the charges cannot flow.
Basically, you will use the word movement of the ions, not the electrons.
Okay.
Most of the students always commit this mistake. They always say that there is no movement of electrons in the ionic compound.
Yeah.
Movement of electrons in ionic compound. That is wrong. You will say movement of the ions in the ionic compound, because they are composed of the ions only, and the ions were made because one atom lost its electrons and transferred it to the other ion, which converted that into the anion. So at this moment there is no free electrons now, they are just ions here. So yes, they will not conduct electricity when they are in their solid form, but they can conduct electricity when they are either in their molten form or the aqueous form. By molten, as you know, when they are converted into their when they are melted, that's the molten form. And the other state, which is the aqueous form, what does it mean by aqueous form?
Dissolved in water.
Yes, dissolved in water. So when they are dissolved in water, what happens to the ionic compound?
The ions split. They're like the ions become separate.
Are they separated from each other just like it, or this other special forces also taking part?
The ions are free to move in the water.
The ions are moving to the water, so you will also say that the water molecule will also create some forces with those ions.
Yeah.
And there is this diagram of this. The water molecules, which are like you can see clearly that these are the structure of the water molecules, and now these water molecules are creating forces with the ions within the ionic compound. Our board book, if you have ever listened to this, ever Oxford, yes, OCR Oxford. So that's one of the book of OCR, because I'm also teaching an OCR board. So there's a picture here. You can see that this structure of the ionic crystal is now splitting into the water molecules, and these water molecules are now surrounding these ions. So yes, that's why they are not splitted. Now what happens to the conductivity of the compound when they are in the aqueous form? Now these ions can easily flow within the water. They can easily flow. So as a result of the flowing of the ions, as a result of the applied voltage, you will need to apply the voltage to have an electricity passing through the aqueous form or the molten form of the ionic compound. But in case of the molten form, there will be no water molecules, right? There will be no water molecules. So basically what will happen in case of the molten form? This solid form of the, let's suppose it is the negative, this is positive, negative, positive, and then positive, negative, positive. In this molten form, these ions will simply be separated from each other. They will be not closer to each other. Now in this case, they can conduct electricity because of the separation from each other, and again when the potential difference is applied, these ions will move to the respective electrodes. As you know, there are two electrodes, negative electrode and positive electrode. What are the names of these electrodes?
Anode and cathode.
Yes, negative is the cathode and positive is the anode. So yes, this happens here. Now about the solubility and the electrical conductivity is linked with each other somehow. The solubility means how the ionic compounds are dissolved in water. So dissolving the ionic compound in water requires energy. You need to apply energy to break apart the lattice structure. Lattice structure is what?
The structure we saw before.
The structure that's
positive ion, negative,
yes,
positive, negative.
exactly. Yes, this one. That's the lattice structure of the ionic compound. So basically, you need to break the structure of the ionic lattice into its scattered form of the ions into split form of the ions, but for this purpose you need energy. Now this energy will be provided by the water molecules. If the water molecules are sufficient enough to break apart the ions, then as a result of this, ionic compound will dissolve in the water. If the energy of water is strong enough, what is basically happening when the water molecules are splitting the ions? The water molecules are creating bonds with the ions. You can see that there are two types of the bonds formed. The positive ions are being bonded with the negative part of the water molecules. You know that there are charges on the water molecules, the positive sigma positive or delta positive sign and the delta negative sign, right?
Yeah.
Basically these opposite charges are creating bonds with each other. Can you tell me what kind of bond is being formed between the ion and the water molecule?
Dipole.
Dipole?
Yeah.
No. I can give you a clue. It's a mixture of bonds. Or it's a hybrid kind of the bond. Yes, a hybrid kind of the bond. So now can you tell me? It's a hybrid type of the bond.
Hydrogen bomb.
No. I think it will not be familiar to you before, that's why you can't tell that name. It is the ion dipole force. This is actually present in Cambridge, but I don't know if it is written anywhere in any of the book of Edexcel or not, but it is there in Cambridge. So ion dipole force is formed. Ion force because of the presence of the positive negative ions, and dipole is because of the presence of the polar molecules here. The water molecules had dipole moments in them. So this is the kind of the force of formed. Now if this dipole force is much stronger than the ionic bond within the ionic compound, then there will be solubility. The ionic compound could be dissolved in the water, but if the ion dipole force is not strong enough to break the ionic bond, then it will be insoluble. Clear?
Yeah.
So that's why we do say that energy is required to break the ionic compound when it is dissolved in water, and that this energy is coming from the attractions, the attractive forces between the ions and the water molecules. That's from where the energy is coming from. There is some kind of attractive forces, and when there is an attractive force, the energy is called exothermic energy or force, exothermic force. That kind of attractive force provides this energy. So, and this word over here, hydration, means the force is coming from the water molecules, hydration. And I have told you now the water molecules are polar, so they are making bonds with the oppositely charged ions. Is that clear now?
Yeah.
Okay. Now about the covalent bonding, and I hope you are much familiar with the covalent bond. How the covalent bond is formed?
So when two molecules share electrons, basically, the
But
electrostatic force of attraction between pair of shared electrons?
The electricity force of attraction between the shared pair of electrons?
Yeah.
No. There is negative charge on the shared pair of electrons. Then how come there will be attractive force?
And the the nucleus of the atom.
Yes, exactly. The nucleus of the atom from where those electrons were shared. So exactly, basically the attractive forces between the electrons of the other atom and the nuclei of the atoms which are participating in the bond formation. They have just included the high overlapping of the orbitals here, or subshells. These are showing the overlapping of the subshells. So a covalent bond formed between two atoms when an atomic orbital containing a single electron from one atom overlaps with an atomic orbital which also contains single electron of the other atom. They should have mentioned single covalent bond because these words show that they are showing single covalent bond. And then we also have double covalent bond and triple covalent bond. And for double covalent bond you will say two electrons from one atom with two electrons of the other atom. That will represent the double covalent bond. So yes, the electrons are shared between the atoms, and then there will be an electrostatic attraction between the nuclei of the bonded atoms and the pair of electrons which are shared between them. So sharing is shown here with the subshells. These are S subshell, these are P, and these are again P. You can either refer them as px orbital and these are py orbital. Will there be any sharing between the s and the p orbital?
There could be. There could be.
Yes, there could be, and there is. There is also the sharing of s orbital with the p orbital.
Yeah.
So this is the sharing of this. Basically, when we say that two atoms are overlapping with each other, they are doing this overlapping at a micro level of the, or at a deeper level of the orbital size. At the orbital level, whenever two atoms are overlapping, they are basically overlapping at the orbital level. So this is the kind of the overlapping shown by different orbitals. Now there is also a topic on the sigma bonds and the pi bonds. Sigma bonds and pi bond. Are you familiar with these bonds?
They have no idea. They have an idea.
No idea.
No, I have an idea.
Okay, so tell me about the sigma bond.
Sigma bonds are stronger than pi bonds. Sigma bonds are basically single bonds. And pi bonds are like double bonds.
And how the sigma bond is formed?
It's only one pair of electrons, whereas in pi bond it's two pairs of electrons.
No.
Sigma bonds, it's end on end, while
yes.
pi bond is like side.
Sigma is right. Sigma is end-to-end bond. But what about pi?
Pi is like sideways.
Yes, good. Sideways overlapping. So that's a major difference between them. Sigma bond is formed by the end on. There are other words as well. If you come across, you can either say end on. You can say end to end. You can say linear. You can say head on. So these all words relate with the sigma bond formation. And for the pi bond you will say sideways, just like you said right now. You can say side to side, you can say parallel, and I hope that's all. Sideways, side, parallel, overlapping. You will say at the end overlapping, linear overlapping, head-on overlapping, and same for the pi bond. You will say overlapping. Clear?
Yeah.
So you will these words for the formation of the sigma and the pi bonds. Okay, here they have shown the example of the hydrogen bond molecule formation, in which the hydrogen atoms are overlapping and you are looking at a covalent bond formation. This is then basically represented by the single lines, just like here in the chlorine they have shown a single straight line, but this is in the within the diagram of the space filling model. It is not the actual structure as a line diagram, because for this you will write H bonded with H like this. It is mentioned here in this other book. This is the other book in which they have shown the bonding, but again no lines are shown. Okay, anyways, so the electrons over here, the other way of showing this overlapping electrons is that you can have this our electrons. Let's suppose if I say that the electron of this hydrogen atom is shown by dot and the electron of the other hydrogen is shown by the cross, then the space where they are overlapping, you can also show them by the electrons on their lines as well. So I will put dot on this line and cross on this line. This is also the other way of showing the shared electrons. Is it clear?
Yeah.
That will be more better, because you can easily find on to which the electron is belonging to. In this case, you don't know whose electron is who, like the dot is belonging to left hydrogen or the right hydrogen, you don't know. But in the one which I have drawn, you can easily find that this X electron belongs to the right hydrogen atom and the dot electron belongs to the left hydrogen atom. That's more accurate, or you can say there are more details in this structure. Now you can also predict how many electrons the two atoms will share with each other. For that purpose, you must have the clear information about the electronic configuration. For chlorine, the atomic number is the atomic number of chlorine is, do you know that?
Repeat the last one.
Atomic number of chlorine it's 17.
Yeah.
So when you will write the electronic configuration of the chlorine, you will come to know that there are 3p5 electrons, and when you split them into its orbitals, you will see that the pz will contain one electron, which means the chlorine requires one electron from the other chlorine atom by sharing to complete its octet. So that's how they are completing their orbitals. So that's the sharing of chlorine. By why there is p orbital shown here instead of spheres? Why are they not showing spheres like this?
Because it's from the S subshell.
Sorry?
Because circle is for S subshell.
Circle is for the S subshell, yes. And P for the P subshell. And the electron ending in the chlorine is the P subshell here. So that's why the orbitals which will be involved in overlapping will be the p subshell, and more specifically speaking, it is the pz orbital. Pz orbital. You have your own option either to write pz in this horizontal way, or you can draw pz in this vertical way, or you can also draw in the diagonal way. You have your option, so you can show the overlapping in either of the ways. Now comes the pi bond formation. Pi bond is basically when there is the sideways overlapping of the orbitals, and yes, they are overlapping sideways, and this is shown overlapping point. But what happens after the orbitals have overlapped? What happens when the orbitals have overlapped? They are basically combined with each other. So this whole area above and below this line, this horizontal line, these cloud above and below this horizontal line shows that the electrons are away from the nucleus. They are not basically on the nucleus. Instead, the electrons are above and below the nucleus. That is also called the nuclear axis. This black line shown here, this indicates the nuclear axis. Nuclear axis is that symmetrical line which joins the nuclei of the atoms. The nuclei of the atoms are definitely present at this central point, but since the atoms are the central point, the electronic cloud structure is shown on the either sides or away from the nucleus. So that's the property of the pi bond, that the electronic cloud density are below and above the molecule or above and below the nuclei of the atoms. They are not symmetrical on the atom. Is that clear?
Yeah.
Okay. So that is about the pi bond formation. Now can you tell me how many electrons are present in the pi bond? When there is one pi bond, then how many total electrons are present in one pi bond?
4.
No.
Six.
There are 2 electrons. 2 electrons are present in a 1 pi bond. Not this. 2 electrons in 1 pi bond. You must be thinking that this p subshell will represent 2 electrons. Is that so?
Well, the 2 overlaps, I was thinking of 2 in each. The 2 overlaps, that's all.
2, okay. You mean the 2 overlaps means that 2 electrons. 2 electrons at this point, and 2 electrons at this point?
Yeah.
No. Basically, the shape of the p subshell is like this one, and they are definitely, they are definitely 2 electrons in one p orbital. If it is, let's suppose it is py orbital, we do know that there are 2 electrons in one p orbital. You can say one electron is present here and the other electron is present here, but in the electronic configuration of the chlorine, you can see that there was just one electron present in the pz orbital.
Okay.
Then why did we draw the structure like this? We should have shown the structure like this, only one part. Why both the lobes are shown here? It is always shown in the form of 2 lobes. These are called lobes. and there is one lobe, then we should have shown the structure like this way, but it is not so. Basically, this shape is the shape of the orbitals irrespective how many electrons are there, either one electron or two electrons. The shape will remain the same in the dumbbell form. Okay. So if there is either one electron or two electron, it will remain the same. In the chlorine, there is just one electron in the pz. If I say it is the pz orbital, it will have one electron, but one electron mean the shape will remain the dumbbell form. It will not change. So now two pz orbitals of two different chlorine atoms, one chlorine atom and second chlorine atom, their pz orbitals, these are their pz orbitals, and they are combining with each other. This pz is combining with this pz orbital. They both have one electron each in their pz orbital. Now, as we know, the pi bond is only possible when they are showing the sideways overlapping. One thing more to be clear here: the chlorine will not show pi bond. Pi bond is not possible in the chlorine molecule. Why is it so? In the chlorine molecule, I'm saying chlorine molecule, pi bond is not possible in chlorine molecule. I have to show you something more here. We said about the PV atomic orbital that they are showing this sideways overlapping like this, but in case of the chlorine molecule, the chlorine molecule is showing the, let's suppose if I say, I have to show you, sorry, this one. This is the example of the nitrogen molecule. For nitrogen molecule, there are three p orbitals which are half filled. There are three p orbitals which are half filled. One is px, the other is py, and the third one is pz. And for chlorine, the px was filled completely, it was paired, py was paired, but pz was half filled, right?
Yeah.
Whenever we have only one p orbital to overlap, then this orbital will only overlap with other pz orbital in the sigma bond formation. There will be sigma bond, not the pi bond. Whenever there is just one p orbital which is involved in the bond formation, then it will go through the sigma bond, not the pi bond. But in case of the nitrogen, there are three p orbitals which are unfilled. Now out of these three, the first one, which is the px, it will show you the sigma bond, whereas the rest of the two will show you the pi bond. These two will be involved in pi bonds. Py will create separate pi bond with the py of the other nitrogen atom, and this pv will show separate pi bond with the pz orbital of the other nitrogen atom. So in total, the nitrogen molecule shows two pi bonds. There are two pi bonds in the nitrogen molecule, and you can see the picture here. If I say this vertical lobe is showing the px orbital, so px orbital has two lobes, one above and one below. And there is another, sorry, I have to show the py, not the px. This is a py orbital, and this is the lower lobe of the py orbital, and this is again py orbital, and this py lobe of the other nitrogen atom. That is one nitrogen atom, and that is the second nitrogen atom. I have shown this with the prime sign on it. Now the py is creating pi bond 1. This pi bond 1 means it is a pi bond between the py orbitals. Pi 1 means it is a pi orbital between the py orbital, and the other half filled orbital in the nitrogen is a pz. I will show this horizontal lobes as pz orbital. This is pz over here for one nitrogen atom, and this is pz orbital of the second nitrogen atom. Now these horizontal lobes of the pz orbital will show the pi 2 bond. This is the pi 2 bond. One lobe is into the plane and the other lobe is out of the plane. Okay.
Okay.
Now that's how we represent one single pi bond. One pi bond has the electronic cloud structure above and below the line connecting the nucleus. One cloud structure is above the line and the other cloud structure is below the line, just like we studied before. One electronic cloud is above the line and the other is below the line of the line joining the nuclei. So that's how we represent the pi bond. So as I told you before about the chlorine, that chlorine has just one as half filled p orbital. So this half p orbital will combine with the pz orbital of the other chlorine atom through the sigma bond, not the pi bond. Is that clear now?
Yeah.
There's a sigma bond, by the way. Okay, so coming back to your book here, chlorine had only one p orbital empty, so it is showing the sigma bond, not the pi bond. Let's take the example of the nitrogen. It is just below this topic. The nitrogen atom here, again as I told you before, has three p orbitals. Now the blue one, you can give names to them, but can you tell me from these three different types of the p orbital which will show you the sigma bond by looking at this picture? The pink one is showing you the sigma bond, because it, as you can see that in the pink one, the electron is just on the line of the two atoms joining with each other. This nitrogen atom is joined through this line, and so the sigma bond electrons are on the line joining the atom. That I forgot to tell you, the electronic cloud of the sigma bond is on the line joining the two atoms. I can say one atom is here and the other atom here, so it is on the line. But for the pi bonds, it is above and below the line joining the two atoms. So they are, now you can see there are two such colors, the blue one and the green one. If I just say blue is a py orbital and green one is a pz orbital. So you can see two cloud structures of both, two cloud structure for py orbital and two cloud structure of the pz orbital, and they are creating their separate pi bonds. They have mistakenly shown only one pi bond. You have to show another pi bond here. It is also showing a pi bond. Is that clear?
Yeah.
Okay. Now within this nitrogen, triple bonded with nitrogen, it means that these three lines are showing three types of the bond. Nitrogen is bonded through sigma bond with other nitrogen atom. It is pi bonded with the other nitrogen atom, and another pi bond with the nitrogen atom. So these three lines represent these three types of the bonds: sigma bond and two pi bonds. Clear?
Yeah.
Now the bond length and the bond strength. Do you have any idea of this topic? Okay. So basically the bond strength is that it is the amount of the energy present within the bond of two atoms. Bond strength is the strength of the bond. It is the energy which is present within the two covalently bonded atoms, that is covalently, it should be covalently bonded. You will say covalently bonded. The strength of the bond when two atoms are covalently bonded, and the bond length is the distance between the two atoms when they are bonded with each other. The distance from one atom to the other atom, that is the distance. So this whole, the space or the distance from one atom to the other is the bond length. So don't confuse it with the covalent radius. Covalent radius is only when the atoms are same and they are just two atoms. They should be diatomic only, mostly diatomic, or in some cases, for example, sulfur, it contains even 8 atoms. So for the covalent radius, you should have the molecule of one element. It is elemental molecule. But for the bond length, it can be the atom bonded with any other element's atom, not the same element. So bond length represents the distance from one atom to the other within the covalent bond. So we have a complete list here, and we do not need to remember these values, but we will need to use these values in our calculations. We are expected to use these values in our calculations. However, what you can expect some of the trend as well, that the bond length and the bond strength values vary. For example, if you consider these first three values, what do you see? The chlorine is changed to bromine and then iodine, which means you are moving down the group. Is it so?
Clear.
And the same goes for the nitrogen. To within the nitrogen molecule, it is also showing some single or triple bond, so that's why the bond strength is increasing and the bond length is decreasing. And for the oxygen as well, bond length decreases and bond strength increases. Okay, so we have studied the strength and the bond length of these molecules. Now our next topic is based on electronegativity and bond polarity, so I will start that topic in our next class. Okay.